Hi everyone, my name is Erica Sweet. I work on the C++ team, and I'm here to share what's new for C++ cross-platform developers in Visual Studio 2022. If you're a C++ developer who is building for or looking to add support for more than one platform, or if you're developing with an eye to open source, then this talk is for you. Maybe you target both Windows and Linux, but your team isn't as familiar or productive with command line tools like Ldb. Maybe you maintain different workflows or configuration files for every combination of target platform and development environment, and you're looking to streamline that process while still supporting a diverse set of tools. Or maybe you only build locally for Windows and you rely on your CI pipeline to check non-Windows builds. If you don't target Windows at all, then stay tuned as we discuss C++ cross-platform dependency management and build and debug a Linux GUI application natively on Windows with WSL. So I'm starting with a Cmake project open in Visual Studio. Cmake is an open-source cross-platform build system generator that's supported natively in Visual Studio and is our recommendation for C++ cross-platform development. If you don't use Cmake, then Visual Studio has remote debugging tools for you that we'll cover in the second half of this demo. One piece of feedback that we received on Visual Studio 2019 was that it could be difficult to reproduce Cmake builds outside of Visual Studio. So to address this, we worked closely with the maintainers of Cmake to develop a new file called cmakepresets.json. That's supported directly by Cmake and can be used to drive Cmake generation and build both with and without our tools. That means your team can use it from Visual Studio, from VS Code, from the Cmake GUI, in a CI pipeline, or from the command line on Windows, Linux, and Mac. Visual Studio's Cmake presets integration is automatically enabled for me because I have the cmakepresets.json file at the root of my open folder. But if I didn't have that file, then I could enable the integration by going to Tools, Options, Cmake, checking Prefer using Cmake presets for configure, build, and test, and then closing and reopening the folder in Visual Studio. Cmake presets is the recommended alternative to Cmake settings and will be the default configuration method in future releases of Visual Studio 2022. So you might realize across the menu bar that I now have 3 dropdowns. The dropdown on the left is my active target system. So because Cmake is cross-platform, I can build and debug this project on my local machine, on any number of WSL distros that Visual Studio will automatically pick up on, or on SSH connections. And these can be connections to servers, desktop, it doesn't matter. And I can target all of these systems from the same instance of Visual Studio. The dropdown in the middle is my active configure preset, which drives Cmake cache generation and corresponds to the Cmake configure step from the command line. And the dropdown on the right is my active build preset, which drives Cmake builds and corresponds to the Cmake build step from the command line. And I can select Manage Build Presets to open up my cmakepresets.json file and take a closer look. In this file, I can define any number of configure presets, build presets, or test presets, which encode the information that I would normally pass to Cmake from the command line. So in my configure preset, that's things like my generator and my build directory. I've already set up my presets file, so I can go ahead and kick off cache generation on Windows. For lots more information on cmakepresets.json, as well as its companion user-level file, cmakeuserpresets.json, you can check out aka.ms/cmakepresetsvs. All right, so it looks like cache generation has finished, but it was unsuccessful because I'm missing a dependency. Cmake cannot find glad. So as a C++ developer, you might be used to copying and pasting dependencies around and resolving any transitive dependencies by hand, or you might be used to platform-specific solutions like a system package manager. And to help mitigate this, I'm using VC Package, which is an open-source, cross-platform dependency management tool for C and C++. So because 1, I have this vcpackage.json file adjacent to my root Cmake lists, and 2, I'm passing the VC Package toolchain file to Cmake. then when I configure this project, VC Package will automatically bring down and build all of the dependencies that I've listed here from source, or download them if I'm using binary caching, and install them in a subdirectory of this project's output directory. So the only thing that I need to do to add this missing dependency is add glad to this list and reconfigure the cache. None of this is Visual Studio specific. It all repros from the command line if you're using Cmake and VC Package, which I'll take a closer look at in just a few minutes. For more information on VC Package, you can check out aka.ms/vcpackage. All right, so it looks like Cmake generation has finished, and this time it was successful. So as I scroll up in the Cmake output window, you can see that the installation of glad and its two dependencies took 73 milliseconds, 265 milliseconds, and the entire operation took less than 5 seconds. And that's because I'm using VC Package binary caching. So the binaries that I'm downloading and installing locally are cached in GitHub packages for other developers on my team to pull down and use on their local dev boxes and to use in my CI pipeline. And before I check in these changes that I just made to vcpackage.json, I'm going to quickly verify that those changes also work on Linux. So all I need to do is change my active target system in Visual Studio to a WSL distribution and reconfigure the cache. And this is a really easy way to verify that any change that you make works on both Windows and Linux locally from Visual Studio using Windows and WSL. All right, again, it looks like Cmake generation was successful. So at this point, I'm ready to check in those changes I made to vcpackage.json. So we added glad to our list of dependencies. I will commit those changes and then push them to the remote. So this project is using GitHub Actions, and I've authored a workflow file that will automatically kick off a CI run on both Windows and Linux on push. So that's getting started now, and we'll come back and take a look at it in just a few minutes. Because Cmake generation was successful, I can now leverage all of Visual Studio's Cmake features. So that's things like Cmake targets view over here in the Solution Explorer, which is a more Cmake-centric way of viewing your code. In-editor documentation for Cmake, which surfaces official Cmake docs in the IDE, and language services for Cmake. So I can do things like right-click and find all references, go to definition, or peek definition on Cmake variables, targets, and functions. As an existing Visual Studio customer, you might already be familiar with the Windows development experience, so I'm going to continue to focus this demo on local development with WSL2. So right now, my active target system is a WSL2 distro, and when I build this project, Visual Studio is actually making a copy of my source tree in the Linux file system and building with native Linux build tools like GCC or Clang. And the reason for this is that WSL2 is a lot faster, anywhere from 3 to 20 times faster, when it's accessing source files in the Linux file system rather than the Windows file system, which can lead to significant performance gains for you. And this is all done using Visual Studio's native support for WSL2, which is brand new in Visual Studio 2022 and will be used automatically anytime that you're targeting a WSL2 distribution. When I start debugging, I'll have the full suite of Visual Studio debugging features available to me, backed by GDB. And to help illustrate this, I'm going to walk through a bug that I encountered when I was prepping for this demo. So if you take a look at the Solution Explorer over to the right, you can see that this project contains 4 targets, including a physics library and a samples executable. So I had samples running as a nice visual demo, but when I went to run the project for a second time, it behaved just like that and exit as soon as it was launched. So it was time to start debugging. The first thing that I did was look for the program's main function or the entry point to the program. And as I was scrolling through main, I got to this update loop that handles all of the input and rendering. And the condition that is checked before this loop is executed is the return value of this window should close function, which checks the close flag of the main window. And because I'm seeing that main window close on me, I thought this would be a good place to set a breakpoint and see what was happening. So I'll set a breakpoint, press F5 to relaunch the debugger. And now I can press F11 to step into this window should close function. And this function is just checking if this window should close flag has been set. So I can run the cursor down to this return statement, and it looks like right now the value of window should close is 0 or false, meaning this window should not close. But because I am seeing that main window close on me, I'm going to set a new data breakpoint that will hit if the value of window should close changes. So I'll go over to breakpoints, add a new data breakpoint for the address of window should close. What's cool here is that I don't need to look at memory at all. I can just reference the name of the variable directly. Press OK, Shift F11 to step out of this function back into main, F5 to continue execution, and sure enough, our data breakpoint was hit. So the value of window should close is now 1 or true. This window should close. So I wanted to take a look at the call stack to see what was calling this function. So I can see that the program is polling for events, processing events, and in this case, that event is a keyboard event, and specifically the escape key. So this program is behaving as if I had pressed the escape key. To fast forward a little bit, I did a bit more debugging and found out that the program was always remembering the last event from the previous session. So the first thing I tried to do was process that stale event before this keyboard event handler was set up, and that did not work. But when I set a breakpoint at that location to debug and take a look at what was happening, the program did behave as expected, which led me to believe it might be some sort of timing issue, and perhaps that stale event was coming in just after the start of the program. So what I ended up doing was adding just a half-second sleep before processing that stale event. So I'll uncomment out my solution, remove the breakpoints that I had set, stop debugging, and then relaunch by pressing F5. And this time, instead of exiting immediately, we'll be able to interact with samples and play with all of our physics demos. Now, what we see here is actually pretty cool. So this is a Linux application running natively on Windows with WSLG, the G stands for graphics, and Windows 11. And you might notice the Linux-based tiling up here in the corner, which indicates that we are indeed running this in a native Linux instance. When I was debugging, I had the full Visual Studio experience backed by GDB, which shows that graphical expression that you just can't really get when you're debugging with GDB from the command line. Another thing I want to underscore is that nothing that I've done so far locks you into Visual Studio. So I'm building with Cmake, VC Package, and GCC. I'm debugging with GDB. So there's nothing Visual Studio specific, and this is a great option for teams who like to maintain a diverse set of tools. And to take a closer look at that, I'm going to hop on over to that Github Actions run where we reproduced our builds using the same tools in our CI pipeline. So here's GitHub Actions. Here's my most recent run that was started 6 minutes ago. It was successful on both Windows and Linux. And if I take a closer look at that Linux run, the thing that I really want to show you is that I'm using the exact same Cmake presets.json file to drive Cmake generation and build that I was using locally. So here I'm passing in the name of my configure preset and build preset to Cmake, which really ensures that your team can maintain that single source of truth that you can use to drive builds both locally from an IDE like Visual Studio, from the command line, or from your CI pipeline. In the same vein, VC Package is downloading and installing the exact same binaries that I was using in Visual Studio for local development when I was targeting both Windows and WSL. Finally, If you're not using Cmake, then Visual Studio has remote debugging tools that you can use to debug on both Linux and Mac. So brand new in Visual Studio 2022 is the ability to attach to a remote process and debug it with the Lldb debugger from Visual Studio. This feature is supported on both Linux and Mac, but for the sake of the demo, my process will be running on WSL. So as I mentioned earlier, with Visual Studio support for WSL2, Visual Studio maintains a copy of your build tree in the Linux file system. So over in Ubuntu, you can see that I'm working on WSL now. This is the Ubuntu 2004 distro. I've navigated into that build directory. I'm gonna start SSH and launch samples. So this is the exact same binary that we are building and debugging from Visual Studio just a few minutes ago. Back in VS, you can use the same attach workflow that you might already be familiar with. So debug, attach to process. We want connection type SSH. The connection target is Erica at localhost. Because I haven't added this connection to the connection manager, I am being prompted to authenticate. And then trust the authenticity of the connection. And once it's done connecting, then Visual Studio will prompt me with a list of all of the processes that are running on that WSL distro. So I want to attach to samples. The last thing I need to do is say whether I'll be debugging with GDB or Lldb. So again, support for Lldb is brand new in Visual Studio 2022, but I could follow this exact same workflow with the GDB debugger. So I will select that. And then when I hit OK, Visual Studio will attach to that process with the Lldb debugger. And when I press pause, I will see the current line of execution, as well as my variables, the call stack, and I'm ready to start debugging. One thing that I want to emphasize about this workflow is that it doesn't matter how you build the binary that you're attaching to from Visual Studio. So you can be building with a custom build script, with Make, with Xcode, with Cmake, it does not matter. You can still attach to it and debug it using the front end of the Visual Studio debugger, backed by either GDB or Lldb. For example, the Office team at Microsoft primarily uses Windows and Visual Studio for their local development, and they're excited to use this feature to remote debug Mac failures. Previously, they might sift through log files to try and understand what's happening, or for a particularly bad issue, they might spin up a Mac machine for native debugging, which is both time-consuming and a less familiar debugging experience. For more information on this workflow, including how to get started with the Lldb debugger, you can check out aka.ms/Lldb. And for more information on other build system agnostic remote debugging workflows, like debugging a Linux core dump from Visual Studio, you can check out our C++ team blog at aka.ms/cppblog. That pretty much wraps up all the new features that I wanted to show you today. To quickly recap what we covered, we used Cmake presets and VC package to build a Cmake project both with and without Visual Studio. So our local builds targeting both Windows and WSL can be reproduced in a CI pipeline or from the command line, as we saw with our GitHub Actions workflow. This can help your team ensure that you maintain that single source of truth and that you're not locked into any specific tools. We also showed how the local Visual Studio development experience now applies to Linux, with Visual Studio's native support for WSL2. It is just as easy to build and debug a Linux GUI application locally from Visual Studio as it is to build and debug for Windows. And finally, no matter how you're building your cross-platform application, Visual Studio offers the best debugging experience for debugging with GDB or Lldb, which can save a ton of time compared to using those same tools from the command line. To get in contact with our team or to stay up to date with what's new for cross-platform developers, you can check out our team blog, which again can be reached at aka.ms/cppblog. Thanks for tuning in.